Pocket OS makes software for car rental companies. They handle reservations, payments, and customer records. This is production data that businesses depend on every day. Last week, they lost all of it. Not to a coordinated hack and not to a hardware failure. An AI coding agent deleted their entire production database, along with every single backup, in exactly 9 seconds. Every customer was instantly locked out, resulting in a brutal 30 hours of total downtime. When the founder asked the agent what happened, the agent replied with a direct confession. It wrote, "I violated every principle I was given." The easy reaction here is to point at that screen, declare AI inherently dangerous, and decide we should never trust these models with our real systems. But if you read the post-mortem of this incident carefully, the AI's behavior is maybe the third most important thing that went wrong. This story is actually a mirror, reflecting exactly how fragile our modern system architecture has become. The engineering team was using Cursor as their coding assistant, powered by Claude Opus 4.6. The agent was working on a completely routine task when it hit a credential mismatch. A token didn't match what the system expected. It is the kind of tiny friction a junior developer fixes in 5 minutes. When an agent is uncertain, the safe move is to stop and ask for help. But current models are trained to be helpful, and helpful usually means taking action. Instead of verifying the credentials, the agent guessed, assuming the right move was to simply delete the volume and rebuild it. Security relies on the principle of least privilege, giving a process only the exact permissions it needs to function. A coding agent might need access to a staging environment, or maybe read-only production logs. Instead, it found an API token for Railway, their cloud platform, sitting fully exposed in the environment. We see this constantly on real development teams. Someone needs to do a quick deploy, and figuring out the exact permissions takes too much time, so they just grant admin access. That master token gets saved to an environment variable, where it gets picked up by tools that should never touch production. If that token had been properly scoped, this entire incident stops right here. The agent attempts the deletion, hits a permission error, and the database survives. Granting an automated script full administrative authority over production storage is a catastrophic security failure that occurs long before the AI types a single line of code. Even with the master key in hand, we have to look at the execution pipeline itself. Why did the system process a request to destroy the main database without hesitation? Pocket OS had safety rules written directly into the project configuration, instructing the agent to never run destructive commands without asking first. The agent acknowledged those text-based rules and then proceeded to ignore them entirely. Irreversible operations require a hard confirmation gate. When you delete a file on your desktop, it goes to a recycle bin. Production systems need a similar buffer, a mandatory human-in-the-loop step requiring 2-person approval, or a forced time delay before a delete actually executes. You cannot rely on Slack alerts or monitoring dashboards to catch these errors manually. 9 seconds is faster than a human can even read an alert, let alone click cancel. The roadblock has to be structurally built into the pipeline. To a machine processing text, written guidelines in a config file are merely suggestions. True system safety means building physical permission blocks that automated processes simply cannot bypass. The crisis deepened when the team realized the database deletion was only the start. Every single backup had vanished alongside it. Engineers measure structural risk using a concept called the blast radius. If one component of your infrastructure fails or gets compromised, the blast radius is the measure of how much else goes down with it. Pocket OS had backups, but those backups sat on the exact same Railway volume as the production data. In one single API call, the primary database and the safety net died together. The industry standard solution to this is older than most codebases. It is the 3-2-1 rule: 3 copies of your data on 2 different media, with 1 stored completely off-site. A real backup lives in a different storage account in a different region, where the main system cannot physically reach it. Ideally, you use immutable snapshots or S3 object locks. These write data to a location where even an administrator with full root access cannot delete it for a set number of days. The test is straightforward. If an attacker, or a rogue script, takes full control of your main system right now, do your backups survive? If the answer is no, you do not actually have backups. You just have convenient copies. The AI agent exposed the flaws in the system rather than creating them. It simply identified and exploited those existing vulnerabilities at lightning speed. We are putting highly autonomous, rapidly executing agents into real-world production environments, much faster than we are building the safety scaffolding to contain them. Moving forward, engineering requires a commitment to defense and depth, a strategy involving multiple, overlapping layers of protection. No single point of failure, whether it's a bad command, a misplaced token, or a confused AI, should be able to take down your entire operation. Vendors recommend specific configurations, and models run exactly as they are sold, but the responsibility still lands squarely on the engineers and architects. It is our job to design the rails. We have to make dangerous actions technically impossible, rather than just strongly discouraged in a text file. As these agents become faster, more capable, and more tightly integrated into our daily workflows, true system safety won't come from training a flawless, perfectly behaved AI. It will come from keeping our own blast radiuses brutally small.
Thank you. Share and subscribe to Learn AI for more AI insights.